But for that, I did. Oh yeah, now it's recorded.
Yeah, I recording. I hope that's okay.
You just hit the record button?
Yes,
yeah.
yes.
It's okay. Now, hey, Nathan. So I just want to have this other perspective, this user perspective also onto the library.
Yeah.
Yeah, but I didn't do anything in that regard yet.
Okay, I see. Yeah, so Berson, what's your experience so far?
Well, actually, I'm more interested in the particles one. So I went through all of them one by one and tried to change the parameters and try to add other things. So far, like, it's really interesting and working well. I mean, I haven't faced any issues yet, except the first patch, modulate strength. I couldn't make that running. I mean, the window is blank in my computer. I don't know why.
Yeah, I think I still need to fix something there. I think that one's broken, actually.
It doesn't work, I confirm.
Doesn't work. Yeah, I will put this into R&D for now and then see
that was the only thing from my end so far.
Yeah, okay. All right. Yeah, so maybe I give you some head up of the system, so and start like really simple. Yeah. And Nathan, you will just add. And whenever you get to questions, just there are more people join, at least one more. Let's see. Okay, so I hope this is working for you, the screen sharing, like this. It's like 4K, so I hope it's like, can you see everything?
Yeah.
Yes.
Okay, yeah. Okay, so this is a pretty simple fuse patch. Yeah, so like to just get a bit through the autonomy of everything. I mean, here you already can also see a lot. So let's get through it like one by one. So what you see here is basically, this is like the entry point to get into the fuse world, which is a draw shader graph, right? And so in this case, it's a pretty simple graph where you have a vertex shader and a pixel shader. So it's pretty much the most simple thing, yeah. And what you see here is you have the position as an entry point, yeah, and you have the color target as an entry point, yeah. And those entry points can be filled with fuse nodes. And so if we take this one out, you see that there's like a default implementation, what you see here. So there's like this red color and the default plane, which is the default thing. Yeah, and so now if we start, for example, you could take the texture coordinates. It's this one. And this one, if we look in here, so one thing you need to see is what actually is the type of the node. Hey, Matthias. So as you know from shaders, there's basically like the normal numeric types are like float, float 2, float 3, float 4. And like in fuse, this is represented by a GPU value, and then it's vector 2 is what you see there, or vector 3 or vector 4. And like in this case, now we cannot connect this GPU value vector 2 to this GPU value vector 4, right? So type conversion is something you deal a lot with in fuse, and this is like one topic we will cover, and that we try to solve with different variations or different patterns. And so to apply this node, there's one cast node, cast float. And this node now already shows like one of the concepts of Fuse, and this is adaptiveness. Wherever this is possible, we try to make nodes adaptive so that they work for multiple types. And this means we only need to create them once for one type, or basically for all types, and not like 4 times for 4 different types, like for float or float 2 or float 3. And so now that we connect the text chord, you see that this node is still gray because this type can still not be resolved. And now we put this one into the color target. And now you see that it can be resolved and that actually the text chord is filled in to the color target, right? And now you see this pretty common texture chord scheme, which you probably all know. And although this is pretty simple, it already highlights a lot. So let me just shortly go into the cast float. This is not now for you to remember everything, you know. So I also show you some inner mechanics of Fuse, which will probably not be something that you will use maybe for further development, but give you some more understanding and deeper understanding of the possibilities. And yeah, so basically one thing that you see here is how this adaptive node works. So like here you see this one is generic, this one is generic, and this one is also generic. And then if we look into this node, which is called an adaptive conversion node because we use it somewhere else also. Like here you see, yeah, basically that we call something that is called mix-in function. And we have this adaptive signature node. And basically, this adaptive signature takes the input value and also reads the output value, right? And then gives back some string. Yeah, and this string then helps like to configure which function to call, right? And with the mix-in function, this is something that calls like, I mean, I hope you're all aware with shaders and blah, blah, blah. If you have any questions, you know, just interrupt me and let me know. Like in this case,
Chris, can I interrupt you?
Yeah.
Because this is getting
too detailed already.
Sophisticated quite fast. Because,
yeah, okay.
I mean, this is a bit crazy.
Yeah.
So cast float, why is it called cast float? If I'm able to convert from vector 2 to vector 4 in order to draw that color. So it means like cast each float in the data type or
exactly.
Yeah,
so basically
okay.
Cast float is like one thing that you have in shaders is when you have a float and you multiply it with a vector 2 or with a float 2, this works, right? And so like the shader is automatic, the shader compiler is automatically like casting the float to a float 2. And with this cast function, we have like the standard operations on how to make one vector to the other vector. Yeah, where we assume this is the most common way of how you would convert this one. There are other nodes for swizzling, which I will probably also cover. Yeah, which is how to do it. But maybe like one last thing on how to maybe look if you want to know what the cast float is doing. You could look in here, and then there's like this shader file, Fuse core base cast. And in the folder, you can find where it is. So this is now just that you know, like all the shaders, this is maybe not so much about the mechanics, but we have a lot of shaders with functions that we use. And if you want to know in more detail what is going on, you can always look into the shaders, right? And this is more like get an idea, okay, what is going on, you know, to debug stuff. And one of those things would be this fuse core base cast. This is the file. And if I open it, we see now all the functions. So you see, and there are basically 16 functions, because this is like from a float, you can make a float or a float 2 or a float 3. So these are like all combinations. And here you could look up, what happens, for example, if I put in the float 2, so which happens here, and I get out a float 4. So this would be the function, right? So and if you want to know what happens, you could pick it up here. You get a float, you put in a float 2, you get back a float 4. And what you see is that you take the XY, the Z is 0, and the fourth one is 1. Yeah.
So
And
it's common that you need W to be set to 1.
Yes.
So you mix in some common knowledge or typically needed behavior, and you put that into. It's not like, okay, cast float just takes. If you have a bigger vector output, then you put in, then the rest gets filled with zeros. No, it's not like that. It's just sometimes a 0 gets added, sometimes a 0 and a 1 gets added, sometimes if you scroll up, which that confused me there, sometimes you do just pxxx. So if I put in one float, I don't get 0, 0 for y and z, but I get xxx. So it looks like it sometimes does this and sometimes behaves a little bit different.
Yeah, I mean, like, this is from our experience where we would think this is the most common thing that you would use for conversion. And this is not so much about the details here. This is more like to make you aware where this functionality comes from so that you can look it up. Yeah.
Yeah, and but of course it's very important to specify this once and to then be able to explain the user, look, behind this name, you can expect this and that functionality. You don't want to look it up all the time. You just want to learn it once and then, So that's why I was just, because you said there are different ways to do it. And if there are already different ways, then I just really want to use the node with that name or with that name, and then know what it does exactly. So behind cast, I wouldn't expect so many different tricks here. But okay, that's just.
So that's a good point. So this is probably something where we should put an overview help patch, to more explain how much stuff this node is doing actually.
Yeah, okay.
And this is probably like one of the things with Fuse, that we try to have less nodes doing more stuff. Like here with the cast, so that it's always, I mean, the advantage of this adaptiveness is that you, for example, could take out this one and just directly connect something else. And then you directly have the position there, without the need to have another special cast node to do this. Yeah. So we try to take the most common cases and make the workflow fast without the need to do too much repatching. And this is one concept. And this is also something that could be discussed. Yeah. Is that, does it make sense, or does it need more explaining? Yeah. Or
probably we can't say it just yet, but it's okay. The cast float node is more or less the one that you typically use to go from one type to the other.
Exactly, that would do the most tricks. And then, like maybe the next thing to look up. So the first thing to be aware is shader files, right? So I already showed you there's a folder with all the shader files where you can look up implementation stuff. And of course, another way to get an overview is to go into the definition of the libraries, which is probably something you are aware, right? And like, this is really the most common. This is like one of the base libs here. Yeah. And one thing that you see here is There are a couple of conversion nodes, something more special. You also find this draw shader graph here, which we just had. You see, okay, there's also like a compute shader stuff. And what you see here is like a lot of swizzle options, or options on how to split vectors and join them again. Yeah. And these are, besides the cast, other possibilities on how to put your vector together yourself. So if we go back to our patch, right? Here we have the text chord, and now it's basically put the XY just to the red and green. But we could, for example, now take the X plus Y. So basically this join node. And here now we can say how we want to fill the vector ourselves, right? So here we can define this. And then there's also, so we could also take the split node, which is X minus. Now we put the text chord here. And now we could, for example, make other connections and set the channels as we need those, yeah, but have them mixed up. Okay. So this is basically the first thing about typing. Yeah, so you can cast for the most common cases, and you have join and split operations, you know, for more defined stuff and more special variations.
Okay, so X minus Y has nothing to do with subtraction. It's about splitting, yeah?
Yeah, it's about splitting. Yeah. Yeah, this was one notion. This is also something, for me, it was like more like, okay, plus is like putting together, so join, yeah, and minus is like separating, so split.
Yeah,
this,
we were probably going through some renaming at some point, also like to align a bit with DL as well, like join, split is more like we are used to using DL, I guess. So, yeah.
Yeah, I mean, I don't know. it's just you need to have an introduction into Fuse anyway. But on the other hand, you wanted to make Fuse at some point a high level, easy to use, plug and play. Yeah, an easy tool to play with, and I don't know. It is probably better to then go with some standard naming conventions so that you don't have to learn stuff like that. I mean, if I read X minus Y, I always think about subtraction and not, if I see that in the patch, I don't think of splitting here. But that's just personal. Probably.
No, but I really think that it's important that we align on the same page.
Okay.
And I mean, we are already established a sort of default, and I think we should.
But how would the vector split look in DL? What is the node here?
If you type split, yeah, then you have.
For vectors, it's a bit different. The naming scheme, we messed that up, I think.
Actually, if you type vector, sorry.
For vector, it's not the name of the operation.
Just get rid of it.
Yeah, it's suddenly the split ended up in the
Vector.
version.
You see that there are two options, vector join and split, and then you can choose the version.
Yeah, I think we copied that from beta, vector join, vector split, this idea. Naming them like that so that we have a vector node, not a split node. Anyway, yeah, that's something that we messed up ourselves.
Yeah, so then it's maybe like in beta, you know, it was like with small and big letters, which was something I liked, but it was not so clear, like also like naming wise, I think. So this is why I came up with another notion. So maybe this is something that we could discuss more, like how to align this, right?
Yeah, exactly. I think it's just a detail. We need to...
Yeah, no, yeah, okay. Yeah, we should move on. It's just...
Okay. Yeah, but I noted that. But this is also what this is for, you know, to get some feedback on what you like and what you don't like. And I hope that is fine. You know, you can ask questions and I will explain stuff. If it's getting too detailed, interrupt me, please. Yeah. But this is more like to find the pace for this kind of discussion, you know, because this is like valuable feedback.
Yeah,
and
exactly.
like, of course, like my background is I have not worked with VL. I have not worked with Beta. I mean, at least not much. You know, so I'm not so aware of this notion, and it's more like, okay, for me, it's all like new ground, and this is sometimes where this comes from. Yeah, so that I'm not, I don't have these kind of established workflows,
yeah,
which is sometimes maybe an advantage, you know, to not think, to more think outside of the box, but sometimes it's not then as streamlined as it could be with a common workflow. Yeah. But these split nodes are pretty important. So I would really like to maybe discuss this in more detail at a certain time. Yeah, and also look like how we could make this, as I said, more streamlined with VL also. But also I think the vector is maybe not so readable. But I get your point. The minus and plus might be misleading here. Okay. So
does it do what we want? We want to have like okay, how do I have to read that? So the y goes into the new x, so which means y. I mean, well, so, is the output exactly what?
Yeah, this
what
is
we would
x
expect,
and this is y. And like here, the inputs are x, y, z, w, and the output is x, y, z, w joined out of that node. Yeah.
Yeah. Okay.
Okay. Okay, so that's basically like about these type combinations, right? One thing that you might also want to see is the shader code that is generated. And so there are different ways to do this, right? So one thing is like these nodes quite often have these like debug outputs where you get the shader code, but also in case of something happens, you get an error, yeah, which should hopefully not happen too often when you work with the system, because like one advantage, of course, for patching is that you make less errors, right? Because the syntax should be right, and this is something that should not happen. So if you get weird errors here, would be cool if you could save the patch, send it to us, you know, and then we can have a look into it if this is a bug on our side or something that we can help to prevent. Yeah, and if you look in here, this is basically the generated shader. Yeah, this is something that otherwise you would have to write yourself. And yeah, so like here you see now this is a swizzling, right? So here we get this, we store the y first and the x value, and then put this one into a float 4, yeah, which is now we set the x. This one will be left 0. So this is pretty much what we patched here. Yeah. Another way to debug your shader is also there's a source code node. And with this one, you can get anywhere in the graph and then just get an idea, okay, what is the source code written so far? So we could also look up the patch here and then look up the source code for everything that is above this thing. Yeah. So here we only see the source code for the swizzle operation. So you see, okay, I take the x from the text chord and the y, and then join this together in the float 4. And this can also help, you know, to debug a bit stuff and get a clearer understanding of how Fuse is doing stuff. Okay. maybe that could also be noted for an hair patch. Okay. So let's get back to a more advanced example with the noise, right? Okay. Yeah, so in this case, something crashed. I don't know why. So it was just F5 and then it was running again. So this is something that happens, like we try to make the system as responsive as possible so that if you patch, it always runs. But there are cases when something crashes and F8 and F5 gets it running again. Yeah, so we already make it much more stable, but there are still moments when it breaks while patching. Yeah, so the next thing maybe is like work with the noise to get more about more other principles and how to work with it. So we have this one is, yeah. So with the noise, this is one example on how we work with types. Like if you hover this noise, you see this is a noise 3D scalar. So this is a typed noise. And this means it gets a 3D position in, yeah, and a scalar out. So like a float 2.
Chris?
Yeah.
Can you zoom a little bit so that we can see the tooltips better?
Wait, this was with control. Yeah.
Thanks.
Okay. Yeah, now it's bigger, right? So you see this expects a vector 3 or a float 32. But there's also another variant of the noise, which is adaptive. So you see this is now not already, this is still gray and it doesn't know which input gets out. So this is generic. This is kind of like the cast node, right? So the implementation of the noise, like Fuse will decide this for you and it will pick it up from the input and from the output. And like here, I could do the same thing like I did with the cast. So I take the text chord and now the first input is typed. So it's a vector 2. And now we take the output and just connect it to the color 4. And now you see, okay, we have this noise value. The noise can now be built because it knows the input type, which is a vector 2, and the output type, which is a vector 4, right? And then it puts out this noise value in here. Yeah. Okay.
Is there any, are all the dimensions used in the same way? Do I have to think about alpha in a different way, or W, or is the noise just done for all the dimensions the same way?
Yeah, it's done for all the dimensions in the same way. Yeah, so you can say, for example, if you, I mean, first let's scale this one. So this is one other thing. We have operators, of course, also in Fuse, right? So this is now the multiplication. And here you again see it's adaptive. It's not typed yet. Yeah, so you can use it for float 3, float 4, and the other types as well. And as soon as we put in one type in here, it already knows, okay, I'm a vector 2 multiplication. Yeah, because for multiplication, it's clear that you need to multiply vector 2s and also get out a vector 2. Yeah. And one other feature of those operators is that they are pin groupable. So you could, with the control plus, add as many inputs, yeah, as you need for this multiplier. So, and we are now going to scale this one. And now the next thing is on how to get values in to the system. So there are different ways to do that. So one way is to use the GPU in node, which you connect and then you can connect something here. There's also a GPU in from float node, which always receives a float and which you then can connect. And this basically makes a vector 2 out of this, where x and y have the same value. So, and now we can scale the noise, and we see more of the noise pattern. The new feature which we just established is that you can also connect CPU values directly to GPU, right? And you do not even need this GPU in anymore to get values, you know, from your computer to this one. But this might still help, for example, sometimes when you have cached regions or whatever. Yeah, so these are still needed in some cases, but most often you want to connect just directly the value. Okay. Yeah, and now if we talk again about adaptiveness of the noise, so just to see what happens. So we could now just take the x value of the text chord and see what happens. So you see, and the noise is automatically adjusting. And this is now a 1D implementation of the noise, you know, which gets one value and then outputs the 3 values. Or what we could also do is, instead of just taking one dimension, we could add a third dimension. So which is what this vector is doing. So it gets a 2D vector, and you can now input a third vector. And yeah, you can just connect if you create an IO box here. Yeah, you get also like control of this, and now you see we can get over this third dimension of the noise. Yeah. So this could also be stopwatch, for example. And then it's animated over time. Yeah. And this would also work the same for a 3D noise. And we think that this is pretty handy, yeah, because you do not need to exchange the noise nodes and whatever, but you can just, if you want to have one dimension more because you think, hey, I want to have this animated, then you just add the nodes on top and just reconnect it and it works. Yeah. And so this makes patching easier, but you have to understand on how to deal with the types and the adaptiveness. And yeah, this is something that we are curious about on how you pick this up and if this needs more explaining, or would it help to have still more distinguished nodes like with the noise where we have typed versions also, or if that is something that is, yeah, working this way. Okay. All right. Yeah. And then any questions so far or comments?
Yeah, I was just mentioning that the library should also explain this text chord node that seems to come very often in the patches, because for someone who doesn't know what a shader is, you see this text chord everywhere. It doesn't really make sense what it is and why you have to use it everywhere.
Text chord and position.
Yeah.
Yeah, I already made notes for some overview help patches, you know, so I already noted like cast, join split, and debugging, you know, to have like some overview patches where we have the notes and explain what they're doing. And I think that should also be done like for the semantics, right? This is what it's called. And to have this for text chord and position, and maybe also explain on how you can create your own semantics. Yeah. Because this is also possible with the draw shader graph, yeah, to get your own values in. But this is something that could be covered probably in another session on how to do that. Yeah.
And will there be a text chord where I can specify which texture coordinates I actually want? Because some models come with different texture coordinates.
Yes, so just to get a more detail about this, if we look into the text chord node, you actually see what it's doing, right? It takes a string constant and then creates a semantic from it. Yeah. And something that you could do, so you could easily take this one here, go back there, and just place this one here. And then it's pretty much the same. Yeah. And if any semantic is missing, or you have your custom semantic, you could just change that here. And so like for text chord 0, you would just put this one in, and then you would, it's still now the same, but like text chord 1, yeah, seems to be all the same currently set. I mean, there's something on, there are a lot of, yeah, I'm not sure, I will not cover this in too much detail, you know, but this is now to just give you some hints of information on how the whole system works. And then maybe like in following sessions, you know, we can get into more details with other stuff. Yeah, so Stride comes with a big lib of shaders already, yeah, and also semantics and whatever. And it sometimes, it can help to look into the Stride shaders, you know, to get some more information on how stuff is working. We try to integrate the most common stuff into Fuse, and also there might be stuff missing. So this would also be a case of feedback, like for example, hey, you missed some semantics, you know, then we could add them to the system so that you do not need to look them up, but that they are just there and in a help patch and easy to find. Okay. Yeah. So now comes a bit more complex concept of Fuse, and this is how to work with functions, right? Because you do not only want to call functions and want to have parameters, but you also want to be able to forward functions somewhere else so that they can be called by another node, right? And one of the use cases which we have here is this FBM. So let me connect this here. Okay, so what is the FBM doing? This is fractal Brownian motion, right? And what it does is you get a couple of octaves of the same signal. Yeah, so you have multiple levels of noise that are put on top of each other. So if we reduce now the number of noise to 1, I guess you are familiar with this concept, right? So we have 1 octave, and then we can add higher frequencies. Yeah, and the FBM node in Fuse is implemented that you can linearly blend with multiple octaves. Yeah, and we also have different implementations of this. Yeah, so it can be additive or multiplicative, yeah, and it just slightly changes the output. But what is more important is that what you see here is the input of this FBM operator is another function, which is in this case the noise. Yeah, and what you see here is that different from before, where I had the noise and I had put in my text chord in here, right? And then have directly drawn the noise. I now put this position into the FBM, right? Because this FBM is calling the noise multiple times, right? So I cannot provide the variable directly to the noise, but I pass it to this FBM operation and then tell this FBM what other operation should be called. Yeah. Is that clear why it is needed? Okay. Yeah, and basically, just that you have seen this quickly, I will not cover this in too much detail now. In another session, we will probably show you how to create those functions yourself. But one thing you see here in the noise is this kind of delegate parameter. And this one checks if you set a parameter explicitly, like we've done before with the text chord, when we have directly passed it to the noise. Or if you do not set the parameter, and then it can be passed, like the output of this node is now not a value itself, but it is a function that returns a GPU value float. Yeah. And this can be confusing a bit in the system, because here you do not see in the output like a function of GPU value float 32, but it's also a GPU value float. Yeah. But this makes stuff simpler to connect and simpler to work with systems, because one thing, for example, you can do with this function, right? You could add now, for example, another operator and then extend this function. So, for example, you could add a plus to this noise output. So now we do not add something, but we will now add a value here. So now you see I add something and the noise gets brighter or darker. You know, so the cool thing here is you can take this thing and actually, yeah, manipulate the function, yeah, or put in your own function. So something that you could do here in the FBM is you could also, for example, take a sign from the FBM and put it in here. Yeah, in this case, it doesn't make so much sense, it looks like.
Would text chord make sense to connect text chord to the FBM?
No, because FBM, this is a semantic and it's not a function, so it does not make sense. Yeah, but we can see if we. Yeah. So this does not work yet. But now when we connect this one, you see that you can still, or you could add another noise or do other funky stuff here. Like, you know, you can build really complex functions which are then called by other systems. And
but text chord outputs a GPU value,
yes,
of vector 2. So this is like very regular. It's like a two-dimensional linear spread in my head, very fine-grained. Mm-hmm. So if I want to understand what the FBM does, I just connect the text chord node, and then I see if I feed all these permutations of X and Y values, this and that, this is what the FBM does. So, but it doesn't make sense. So what's wrong with this idea?
The thing is that FBM expects a function, and the text chord itself is not a function, it's a value. Yeah, and that therefore it's not working. Yeah, so if I put,
I guess the idea with the function is not understood by me. I mean, I know what a function is, and I also know that the delegate concept, but I don't exactly know what the FBM feeds upstream. How does it call the function upstream? Maybe I just don't know enough about this Brownian motion thing, how it's meant to work. So I would have just played and connected everything together, and it would be type compatible now. Like, I would be able to connect it, but it wouldn't make sense.
It wouldn't make sense. And in this case, it's more like JavaScript than like C#. you know, you can do stuff that doesn't make sense, for sure. Yeah.
But maybe this is relevant and we should consider it, that we should at least find ways to communicate this or implement some warnings or to implement, I don't know, maybe some interface magic, you know, in a way that you can't connect everything there, just to, because not everything makes sense. So we should find a mechanism to do that, to prevent anything.
Yeah. So basically now what we do, we connect the text code there.
Okay.
Yeah.
Right.
So something is happening. I don't know what. Let's see.
Okay.
I guess it creates a function from text code, which is called and which just returns text code, right? So it doesn't make so much sense.
It probably runs the noise using the input.
No, it doesn't run the noise because the noise is not feed in. The noise should be the function. Yeah. So the FBM is just a for loop calling the provided function a couple of times and then saying like how values are put together. So it doesn't need to have any noise. It just needs to have a function.
Yeah, sorry, but no, I think that it looks like there's a gradient there, no?
I think it's, yeah, maybe there is.
Maybe it's just taking the X. I don't know.
Yeah, but if we look in the shader code, let's see what it does. So basically this is the FBM function here. So you see, and what you see here is this is the function that we pass over to the FBM function. And this is something that Stride is doing, yeah, Fuse is doing. So Fuse is basically taking the node that you provide, like in that case, the stream text code X, right? And it also provides a parameter which can be used by the function that you put in. Like for example, for the noise, I will just reconnect it and then we will see, yeah. In this case, you get an argument, but you not even use it. You just directly output your semantic that you have here, right? So it's a function, you build a function from the value, but it doesn't make much sense, yeah. But it's it in itself as operation, it's valid. And what you see here is that this function then here, which we have wrapped like our patch into, is then called in this for loop for the number of octaves, yeah. And now you see a bit like what happens in this FBM. You get an input position and then you call something. And then, yeah, basically here you see that you scale the position and the scale gets also changed with the lacunarity value. The lacunarity is, for example, normally 2, which means like you double the frequency with every octave. And this is how you put like for every part of the for loop, a finer detailed signal on top. Yeah, this is what you do. And this makes sense not only for the noise, but for a lot of operations, but definitely not for this function where we put out the text code. Yeah, but this is how programming is. You can make stuff which doesn't make sense, but in this case, the system still makes use of it. Yeah, and makes it working. And now if we get back to and input the noise. So now we have something that makes more sense. And yes. So you see now Fuse has wrapped up the noise node into this function here, right? And you get this argument. And this argument is now, as you see here, sent to this kind of noise function, which is here the gradient noise. And all the other operations here are just operations to scale the noise, to do some amplitude, right? Or frequency changes or gaining or whatever. Yeah, so these are, but here you see this is where we really call the noise and the other stuff is scaling and calculations on the input and output values. Yeah.
I guess I now know what I would like to connect to the FBM.
Okay.
an identity function, which is a function that goes from x to x, from whatever, alpha to alpha. Like you hand it a 0.7 and it gives you a 0.7 back. Then if I can connect this identity function to the FBM, then I know what the FBM itself does. If I don't have any noise connected, I directly see the just the pure FBM without any contribution of the noise node. You know what I mean? Can I do that?
Yes, you can do that. Let's see. Like this.
No, that's not what I meant. I meant if you go into the shader code, look here, this small function where it takes arc result blah 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 something, and if it would return just that, you know, if it would just return that float that it got as an argument, you know, then this would be somehow the identity function. It would call that and would input p my scale blah blah, and it would get just that back. And
but it cannot, because this already has like a different dimension than the output.
But I don't know how I would do that as a user. What I would like to do is to have a function float that returns a float and takes a float. You know, does it make sense?
Yes, I understand what you mean. What you want. Yes, so it would be possible. I mean, you could take the FBM and then put in I would have to see if I could patch it.
Okay.
Yeah. I will write it down. This is a more theoretical thing.
Yeah. Okay. Just identity function of what of GPU value of T. Like you can use that for different.
Yeah, I have written this down, and okay. Yes. Yeah, so this is basically what I wanted to cover today. Yeah, like in terms of showing stuff, of features, right? So if we repeat again, it's this concept of adaptiveness. It's this kind of type conversion, you know, with the cast float and with this swizzle stuff. And it's this way of using functions, yeah, which we will cover in more detail, because also signed distance field and ray marching, of course, builds heavily upon this, yeah, where every SDF is actually a function, where you put this stuff together, yeah. And yeah, so now it would be more like open for discussion, like questions that you have, also suggestions how we should structure these workshops, maybe more for the following times. Is that cool, like how we did it today, and we cover a topic like at the beginning of each session and get more details and answer questions? Or are there any other suggestions on how to do it?
I like this format of focusing on one part on each session, and also for the documentation, it's easier to follow for the users.
Yeah.
And going back to the FBM, so in the case of the curl function, it works in a similar way, no? It's expecting other function.
Yes.
Yes. Okay.
I think now I know why the sign wasn't working, by the way.
The other one, no?
So if we connect this one, no, yeah. This was the L one. This one. Yeah. So now it's working. Yeah. Because you need this kind of delegate thing. So this was what the noise has this one by default already. Like, and the delegate parameter override looks, do I get a value in and then I execute this function directly, or do I not get a value and then I, so to say, build a function, or I pass the noise as function itself? Because basically noise is a function, right? It's clear, it's a kind of process node which receives value and returns something. And if you do not put something in everywhere, like in all parameters, it basically still is a function. And it is kind of a reduced function. So if you kind of see this kind of process with this many parameters, like most of the parameters are set. Like if we go back into this FBM thing, all the other parameters are set with defaults or whatever, but this one parameter is not set. And so this one is the only parameter that needs to be set by a later operation. Yeah. And this FBM, or maybe, yeah, I will show you something else to maybe get to this delegate mechanism in more detail. But to highlight this, we try to mark all the pins which can be, let's say, forwarded. So to make this a function with this kind of tilde thing that you see here before the domain. Yeah. So it's a bit, this is something that is Fuse kind of grammar or whatever, you know, so it's not like native VL, but we try to come up with this notion, you know, so that you see, okay, this is something which is a function. And yeah, so with this delegate parameter, you can make any node a function, so to say. Yeah, so this is like this kind of delegate thing that you have in VL. Yeah. And so as we do not have this kind of graphical input, we have this kind of node to kind of build a delegate out of this. Yeah. And this is definitely something where we're thinking, is this so user-friendly? Is this understandable? Yeah, but it's totally flexible. It allows a lot of stuff. Yeah, and this is maybe something where we can look up with the VV devs to maybe find a more visual, nice representation to kind of implement this. Yeah, which makes it a bit more understandable. And yeah,
that's something that was lying on my tongue all the time, because this function thing, I mean, it's almost the same as a delegate in VL, and VL has this nice other kind of dashed line where you know, okay, this is something else but a value or a reference that you pass over this.
Yeah.
And from a learning standpoint of view, it's really important, in my opinion, to have some common way of looking at things that goes to the joins and splits and to the function things. And I'm not sure what this means for the devs, or what kind of stuff needs to be done. It also that you put a tilde for pins that you actually need to set is something that makes sense, but you have to search each pin. Is this something that you need to put in yourself, or maybe there's a different way of immediately make it visible that something needs to be set here? So yes. Regarding usability, this is something where some love is probably needed. But otherwise, this is cool, what I've seen until now. This is really cool.
Yeah, so it's definitely like we build this kind of structures around the possibilities that we currently have in VL to express stuff. Yeah, and so we have to put some stuff in nodes still. And we are in discussion with the VV devs, and this discussion is also very fruitful. Yeah, so like, for example, this thing, like before, like all our patches were covered with GPU ins, you know, which we could now get rid of. Yeah. So this is already like a small feature which simplifies a lot of stuff already. Or this tooltips, you know, which we are currently working on, you know, so that you can get a preview out of like most of the GPU nodes, you know, and we really try to make this useful, like that for any kind of operation. Like, for example, in ray marching, you would get a ray march preview of your 3D node, yeah.
Chris, why you didn't use the last version then?
Yeah, I had dinner and family time and whatever, and didn't want to stress it and wanted to have something working for sure.
Yeah, maybe I can show something.
Yes, yes. Just let me finish this, and then yeah, Nathan can give you some overview of the latest features. But this is also why we want to have your feedback here, so that we can, when we talk to the VVV devs, you know, have a clearer perspective on how to implement this maybe natively in VL. Yeah, so, and not only have like our opinion and our view on how to do this, but also have like a broader perspective on how it is perceived. Yeah, and one last thing.
Just a quick idea. Can you, when a node gets turned into a function, can you show that in the tooltip? So
Yeah.
does the tooltip can have knowledge about this, so that you can't, understand it at least when you hover over it?
Yeah,
the output,
good point.
That you see it there. Oh, there's some parameter missing. It's a function.
Yeah.
That
Yes.
would be a quick, just a quick fix. That, yeah.
Yeah, that would be a quick help. Yeah, we definitely want to make it possible to preview also these functions. And then we want to insert like default parameters so that they are invoked and you can still kind of get an idea. But it would probably make sense to show some additional information here. And yeah, we would think about that. Let's see. It's not working. Yeah, that's something I will show next time to get maybe a bit more in detail into this functional programming approach. Okay. Yeah, so back to that example. Yeah, so if you have still questions here or recommendations,
no, just regarding the functional stuff, I would have more questions, because there's always an input type and an output type, and I wouldn't know what GPU value of vector2 means. Is it saying after calling the function you get a float2, or is it saying I give you a float2 and you know what I mean? It just probably just doesn't say anything about what is going upstream, what type. Is that correct? So what's flowing from FBM to the noise is somehow not expressed.
yes, that is true. That is true.
It could be anything.
It could be anything. Like if we go into the FBM, let's have a look. Yeah, I would have to look it up.
Okay. Yeah.
But basically, as you see here, like the invoke gets abstract GPU value, so it doesn't know about the type. Yeah. So in this case, it's more like used internally, and you have to know a bit of how to use it, of how to utilize it. It's not typed on that level. Yeah. Because even you can also have like multiple parameters for the delegate. That's all possible. Yeah, but it's looking ugly in the patches. Yeah.
Probably I can make sense of it. I can go to the noise node and look at that first pin, first input pin, and then I know it needs this type.
Yeah, we will make a session where I will go in more detail and I will prepare patches, and then hopefully this answers more stuff. Yeah. Okay. Yeah, maybe Nathan, you want to show some tooltips now?
Yeah. Okay, let me share my screen. Yes, since a couple of days we are reworking the tooltip. Boston implemented also changed the behavior for the DR tooltips so that they when you pin them to the patch, they look slightly different. They don't have any information. They just present the row value.
Nathan, can you improve the audio quality somehow, magically?
Just turning down the fans of my laptop. You know what? You can go there, and I can use the phone.
A bit louder. I heard you, but pretty quiet.
How do I wait? Hello, hello, hello. Wait. Okay. What about now?
Yeah, it's for me. It's good. Yeah, working.
Okay. So yeah, we understood that the tooltips are really essential. There will be a key component to Fuse, to VL in general, but especially to Fuse. So let me show you an example of some patch that I was working on. Yeah, we are trying to find a mechanism to really allow us to freely implement tooltips, custom tooltips for each pin, for each node, for each pin, and then make sure that they get propagated across the graph. So here, for example, as you see, if I hover with the mouse, I still have my normal tooltip with all the information, but as soon as I pin it in the patch, it's just a clean visualization, it's a monitor of the data. And this is really cool now because you can really follow up. Okay, these are my chords. This is a domain repeater, which means that it takes those chords and in this case, you wrap them. So this is what I'm doing. And then I have a box SDF, which basically use those coordinates and evaluate a box from each one inside each one of the space. So like here, you clearly understand what is a sign distance field, because as you see, that's the box. The black one is the box, and then so where the black ends, that's the surface of the box, and then which is 0. So distance field means distance from a function. So the function is the box, and these clearly represent that if you get away from it, the distance increase, so the value will grow. So it goes towards 1, no? and beyond 1. And here we don't see, but this is a continuous function. So inside is negative. That's why it's sign distance field. So the 0 is the surface of the function, and minus is inside the function, and plus is outside. It's the distance from the surface. We can describe it like that. But it's really cool because you can really play a bit and have a visual feedback, and then you can combine. Now we are making sure that, because in Fuse there are many, as Chris mentioned, there are many adaptive nodes that provide some functionalities that work in many different domains. So you never really know exactly for this node, you never know, you never had one way to look at the data that they are handling, because once you could pass like a 2D data like this one, and then you should see a relevant tooltip like one of these. But then if you use it with a 3D data, this node should present itself and the tooltip in a different way. So we are managing a way to that these nodes pick the most relevant tooltip from the context where they're used. So they check where they are connected to, and they pick the most the closest tooltip that is defined, which will probably be the right domain to display data in. So it's coming. Basically tomorrow we will have this. So and then a Sketch also 3D version for it. Still debugging stuff, but just to show you that it's really cool because this is a 3D sign distance field. And as you see, you can really check, you have really a good feedback, and you know exactly what's happening at every stage. Is just amazing. You really know what every aspect of your graph does. So it's probably recompiling. Yeah. So
it's this type is again what's coming out of cylinder SDF.
GPU float 32.
And the other SDF, it was also GPU value float. So it's a completely different topology. The floats are used in a completely different way, but they all share that they are just floats. They're just bundled together in a different way. No, these are all just distances to a surface.
Yeah, the output of a sign distance field function is a float.
But they are bundled in a different way, you know, and sometimes in 2D and 3D.
But there are different versions. Like as you see, there's this is the 3D version. There is a 2D versions, because the domain changes, no? So obviously every sign distance field function return gives you the distance, but then you could feed as an input a 3D position, like we are doing in this case, or you can feed a 2D position, like in the other way. So the output, this represents really what is the real output of this function.
Yeah.
And so basically that means in the tooltip, there's like a little ray marching shader, which evaluates the shader till this point and then visualizes it. Yeah. And the idea would now then be like if you have the lerp function between two SDFs, which makes total sense because you want to blend between two SDFs, then the output of this lerp function is of course also an SDF and should be visualized as such, right? And this is like where we're now building the tool chain that we look up, because this is something that will also come in following sessions. Like the graph is not only a functional graph, but it can also be enhanced like with meta information, like with tooltips, or also with resource information. And this, for example, already happens internally in Fuse. Like, for example, when I have this mixin function, I add a resource to the system telling the system I need this include file, yeah, or I need this type declaration or whatever. And this can be also used at other stages. And here, for example, we will use it for tooltips. And
we are adding the tooltip here. So for this node, for this output, we are defining a code texture tooltip, which is, again, it's one way to render data basically into a code. But yeah, we are still working on this system. But this is, for example, is a sketch of a possible head patch. No? We are also sketching those. Yeah, maybe I can show what we had in mind. Like we prepared some like how to patch with title, scope, and some maybe like description of certain part of the patch. And here you see the process that you're describing. So this could be one of them. Then the reference, that is more like, the idea is that every node in Fuse will have a reference patch, in which there is just a description of the pins and or more information about what it is and what it does. Also with, I don't know, links from Wikipedia in case of noise, for example. You might be interested in knowing a bit more about, I don't know, where this function come from or whatever. This is more like a technical description of the node, the functionalities, not considering the context. And how to is maybe it could be like some patch where you explain how to use the noise to create something. No? These are the ingredients, and the how to is like a recipe in cuisine. Then you have explanations where we will probably explain like some principles. Again, this is just copy and paste this patch. It's not really relevant, but we are trying also to define some guidelines for the help patch, different kinds of help patches, so that as soon as possible, we would like to share this task with all of you who is interested, to prepare as many as help patches as possible. But following certain guidelines. And actually, we are really interested in also, like, from you, Matthias, I guess you will have a lot of suggestions for this kind of material, how to structure it properly, which is not even strictly related to Fuse, but would be also just finding common layouts, the most simple and clear layout of the patch, how to engage in different ways, like what is an explanation, what is how to reference, how to structure differently the patch in order that it simplifies this process of learning. Then I can show, so this is something that we added like last week, proper integration of fluid. Sorry, Chris, I'm just throwing stuff in.
I think it's good. This is more like to give you a preview, of what's coming up in the next sessions. And of course, you can also give feedback on what you're interested in. So we kind of want to build up the knowledge, but then unto a certain point, we can just open up the complete spectrum.
So we simply, we took the fluid from a version that I already implemented for a project 2 years ago, but now we opened up to Fuse, really, because now, for example, the obstacles, we can use the power of Fuse to create obstacles. Like right now, for example, you might see that there are some sign distance field defining the obstacle from the fluid, for the fluid. So you might see the particles avoiding certain areas, colliding with them. This is defined by these, okay, by our sign distance field. Again, if I, for example, maybe this is cleaner, right? Yes. Now they stay inside because I inverted the sign distance field. So they stay, you see that they're colliding with something, no? That something is like a blob. We can, I don't know if we can, we can see something. We need to implement proper debug for this kind of mode, but it's like a blob of the combined, all these three shapes combined from this kind of deformed blob. And now that's what is constraining the fluid inside, no? They collide with, so it's really cool because you can just develop your knowledge about SDF in Fuse, and you can use all of that as obstacles, or you can use like Let me show these.
Yeah, so
This is
SDF can also be used, for example, as collider in the particle system. You know, so you can have an SDF sphere or box or a combination, also repeat, and then it works also for collision.
So you can have this, well, this is a random texture. We will need to put something meaningful. You can use texture 2D vector field to push the fluid. Now it's operating into this cone, basically into this projection of this texture. But basically you can interact with vector field in the fluid. You have spherical impulses that you can debug as well. So you're emitting velocity, and we are working into integrating more and more. And then again, the output of the fluid is like it's a 3D texture 3D vector field that you can directly use as a force into your particle system. So we are really trying to make as generic as possible this, because in a way we always deal with the same kind of GPU resources and content, and it's just the same, the same concept. So it's quite easy to make use of them in different scenarios. So yeah, what else?
Yeah, maybe show a particle patch with some.
That's your.
Okay.
This one that I just did half an hour before. Here you can clearly see now, like the mapping from the domain to the codomain of the noises. So here we take the texture coordinates, which is a float vector 2. And here we take just the X. So to these noises, we are providing just the X. So, and then obviously we have a noise, which we have a variation over one coordinate, one dimension. This one we just feed the vector 2, and we have as a result, because this is a 2D scalar, we have a noise value in any position of our 2-dimensional space. Here we feed the 2-dimensional space, like exactly like the UV coordinates, but we want to have a vector 2 as an output. So in every point of this space, there would be a 2D vector. And this is the version of the 3D version of it. We append the Z, which is like time in this case, but it's just another dimension. So the noise as an input, as domain as a 3D coordinate, and returns. In this case, we just want to have a float as a return. So this is, again, is represented as a square, but you could imagine that you could have a volume. Each point of this volume has a noise value in it. And this one is the same, but you can produce a vector 3 in each point of this volume. So we are working in implementing more and more of this tooltip. Like, for example, you could have a volume representation of this space that in which you are producing this noise. So yeah, that's why I say that it's really important, this tooltip chapter, because a lot of Fuse is really about finding ways to look at the data. Everything is in buffers. In GPU is like, it's really about how you interpret the buffer that allows you to use the data in different domains and combine them together, come up with algorithms. So it's really important to have a clear vision of over the data, and tooltips really help in that. That's it. So you want to show something with the particles?
Yes. Yeah, maybe one last sketch, because so far you've seen like more dry and like maybe better for teaching. Yeah, but this is now an example where you see like particles together with signed distance field, right? And what you see here is here you also see the preview of the signed distance field, yeah, which is fed into the particle system. And like here you see there's an SDF collider, which gets yeah, the SDF and then applies collision to this. So you can say like, okay, how much bounce is there? You know, so it can be more bouncy, or you can also add roughness to the surface, which means like the particles are not going straight, but they get some kind of random vector, you know, to simulate a rough surface where the particles spring more random. But what you really see is that you can build with this SDF approach really complex geometry, kind of, which is actually not geometry because it's just a formula. But to make this like as kind of real, like with real meshes and bouncing particles from it, you know, is far more challenging than this kind of stuff here. Yeah. And so with this SDF, you see this is a round box and then merged with a plane below, you know, and you can do, yeah, interesting stuff in physical experiments, pretty complex stuff. Yeah. So it's really interesting to play with it. And this is really like the idea to not have too many concepts, but have kind of rich concepts. And like with this SDF, to really explain it once well, like how to work with it in terms of ray marching. And then like Nathan already said, like apply it into different topics, you know, and once you've understood it fully, you really say, okay, how can I build, like, for example, complex force fields for the particles or other stuff. Yeah. So this is a bit looking ahead of what is going to come. And this is something we're currently working with. We definitely give a more detailed view on this compute system, which is behind the particle, which really makes it easier because you do not need to take care of creating buffers and stuff. And like Fuse can make all the resource handling. We're currently looking to extend this also to textures. So our goal would be to also make the fluid system like even more simpler to recreate this, and also have nodes for like fluid operations like diversion and advection and whatever happens there, so that this gets also more playful. Yeah, and that you can it just makes it easier and less scientific to work with this GPU constructs. Yeah. And also much faster because there's so much boilerplate still involved with shader, when you work with shaders, which just gets in the way of just designing. You know, you just want to connect and play and not thinking about, okay, how many textures do I need? Are they double buffered or not? And you get a new parameter and you get another texture and blah, 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 blah. And then something that you just want to see immediately takes you half an hour to patch. And yeah, I think so far, I mean, like Nathan and I guess me and also Carl, we're really amazed currently, like how much fun it makes and how much simpler stuff gets. So, and we hope we can spread that soon over to you. Yeah, so let us know if you have any more feedback or questions, or also recommendations for the next session, which will then be most likely next Wednesday. So this will be kind of the Fuse Day every Wednesday at 8.
It looks super great. Also the help patches and wow. I mean, this particle simulation and SDF stuff. It's just really looking in a very good shape already. Very polished, I would say. Cool to see.
Yeah, thanks. All right, so then Nathan, if you don't have anything to add, I would say that's it for today. we're going to prepare another topic for the next session. Yeah, and then again, keep you updated on the latest development and are open for questions and discussions. Yeah, and yeah, so happy patching with Fuse, and use the channel if you have any questions. We try to get back to you and support you on getting forward.
I think we're gonna push also a new version after the call, because I'd like you also to have a look at the tooltips, or not, Chris? We can do it, no?
Yes, I'm not sure if like the 3.4 should be up before doing that, because this is still on TeamCity. I mean, this is one of the questions. Like, it's definitely that we try to make the NuGets like more stable. You know, like when we have a feeling, okay, this is now a version which is kind of working. Yeah, then we make a NuGet. And it can be like, if you get the latest state from the repository, that some things are broken or not working that stable, you know. So like development is currently pretty fluid with this thing.
So fix the new release, please, Sebastian.
Okay, sure. There's no error, nothing red there, but yeah, okay, this failing test will be.
Yeah, but I totally am on your side, but it needs to be on the website. I think that's the only thing that
Okay.
I'm concerned with.
Sure.
Yeah.
Mm-hmm.
Cool. Then see you soon.
Yeah, see you next week. Bye,
Thank
guys.
you.
Have fun
See ya.
fusing. Bye.
Ciao.
Ciao.